That's loud.
That's
Okay.
all.
Can everybody on Zoom hear me?
Right now.
Hello? Cool.
Okay, let's first introduce the speaker. Ellie is a final year student, PhD student from NYU. And her PhD pass amazing talk on crypto conditions for efficient testing of distributions and quantum states. Welcome.
So yeah, hello everybody. Today I'm going to be talking about crypto and verifying distributions. And I'm going to start by just going through one motivating example, which is verifying quantum advantage. But our results are going to go beyond just quantum advantage and anything that verifying distributions could apply to. So in the quantum advantage setting, Ives, let's say, has just gotten their new quantum computer. She wants to show it off to everybody. So she's like, "Hey, check out my new quantum computer. It can do all sorts of cool stuff." Now we're all looking at Ives and be like, "Oh, sure, that looks like a quantum computer." How do we know that she really has a quantum computer? She could have just been using classical computer and just saying that it was quantum. And in general, companies, have their quantum computers that they might be doing quantum stuff with, or they could just be faking it all with classical computers. And we would really like to know whether, Google or IBM or whatever are really using quantum computers for whatever that they've really succeeded in building quantum computers. And so one kind of way to handle this is something called a proof of quantumness. So a proof of quantumness is a interactive protocol between a verifier, represented by this lamp, and a quantum computer, such that if a quantum computer is running the protocol, then the verifier will be able to say, like, yeah, you're really a quantum computer. That looks right. But any classical computer, any classical prover should not be able to convince the verifier that they're not. The verifier should always be able to tell that it's interacting with the classical computer. And so proofs of quantumness are something that we do know how to build from various cryptographic assumptions. So in particular, like learning with errors. Um, and also from hardness of factoring for classical computers and stuff like this. But in general, running these kinds of protocols is very expensive. At least they're too expensive to be done on today's hardware. Here are a bunch of the citations for various different protocols for proofs of quantumness. As you can see, they go off the screen. There's too many. But we can't really use these in practice. And so instead, what people do is practitioners often consider like a weaker form of quantum advantage, which is something called a quantum advantage sampler. A quantum advantage sampler is not like a protocol, but it's just a single distribution that can be sampled by quantum computers, but such that it cannot be sampled by classical computers. So that is, every single classical samplable distribution should be statistically far from the quantum advantage sample. And so some examples of this include random circuit sampling or IQP circuits or boson sampling, and there are many others. And in fact, several of these have actually been implemented in practice, or so people claim. Now, they claim this, but unfortunately, there's no way to tell if they're telling the truth, because there's no way to verify that samples really came from a quantum advantage sampler. At least there's no known generic way to verify whether the samples we've been given really came from like a random circuit or an IQP circuit or something like this.
Can you give us maybe briefly some intuition for what these distributions are and what are the distributions over?
Yeah.
Discrete space.
So, for example, like random circuit sampling, this is just the distribution is over 0, 1 to the n, so n-bit strings. The distribution is you sample some like long quantum circuit, you run it on the all 0 string, and then you just measure the result, and that's going to be the distribution, just the measurement results. This should be hard to do classically, and we can do it.
What type of quantum circuit are you sampling? You said you run some quantum circuit on zeros?
So yeah, whatever framework you have for quantum circuits, you could just pick a random one and then run it on all zeros. And people think that different versions of this should be hard. But these are like long strings. Right. And so one kind of solution that we could hope for to the fact that there's no generic verifier for quantum advantage sampling is to just be able to verify distributions. So in this talk, we're going to be talking about like the task of distribution verification, whereas you're given some input, which is a description of a distribution, as well as some number of samples from that distribution. And your goal is to test whether those samples really came from that distribution. Okay.
And how are you representing this distribution?
So I will get to it. For the purposes of this talk, it's going to be as a Turing machine. But this is the generic task. You can imagine any sort of representation.
It's also possible like to have like classical discrete fail base there.
So these are distributions over classical strings. So there's always some like really massive classical description of them. And even for like the random quantum circuits, there's a classical description, which is just the description that I gave you, which is pick a random quantum circuit.
And these are Turing machines for PMM, for CDM, or is that?
So these are Turing machines that sample it. So they'll take in a string, a random string, and they'll produce the distribution. So
it's a no input machine, just a random tape.
Yeah. Takes in a random tape and produces, then its output distribution, like the output string is going to be the same as that distribution.
We follow from that distribution. Will be a sample from that histogram, is what you're saying? Are you representing so you have the samples x1 through xt, but you're saying test that these samples x1 through xt came from some distribution. You're saying that distribution itself is represented as a Turing machine.
Yeah.
And the interface of that Turing machine is you give it a random string, it will give you a random sample.
Yeah.
Okay, so it's really you're doing sort of two sample testing rather than goodness of fit testing, where you assume you have a bunch of samples and another bunch of samples, rather than traditional goodness of fit testing, which is you have a distribution represented in PMF or CDF and a bunch of samples. I'm just wondering which of these two your talk is focused on, because in statistics these are different, considered to be different problems.
So the talk is focused on specifically. So I mean, distribution verification right now, I'm not specifying it, but the talk is going to be specifically focused on. I'll define the task later on.
Okay.
But it's going to be like given a description of a Turing machine and a bunch of samples, see whether those samples were produced by that description of the Turing machine. So there's no description of like the PDF or.
So basically given a sampler and given samples.
Yeah.
Okay.
Yeah.
I guess we'll see the formal definition. What it makes the test.
But this right now is completely generic to however the distribution could be represented. And so, the idea is if we had distribution verification, then we could verify quantum advantage samplers. Because given samples from the quantum advantage sampler, the verifier will accept. And since every classical distribution is statistically far, given samples from a classical machine, the verifier will reject, which is great. And I want to note that this kind of security is just only going to be possible against uniform adversaries. That is where the samplers are classical Turing machines, not circuits. Since otherwise the classical machine could just hard code an accepting output. So all of our results will be in the setting of uniform adversaries, but that doesn't mean anything to you, then don't worry about it. So this has been very well studied in the setting of property testing, and the field of testing properties of distributions within sample access. And so in particular, the kind of property testing version of this is the identity test, which there are a number of works for. which is very related to our notion of distribution verification. And I'll say what an identity test is, and then I'll talk about the differences. So an identity test for a distribution G is a verifier var, such that given samples from the distribution on the samples of the distribution, the verifier should accept with high probability. And for any other distribution G that is statistically far, given many samples from G, the verifier should reject with high probability or accept with low probability.
What's plus? T. What's T?
Yeah, that's T. That's
something.
And this is great and kind of seems to be exactly what we want. But there are going to be two problems here, which is why that make this like not quite right for the notion that we would need for, say, something like verifying quantum advantage samplers. So the first problem is that identity testing is like very inefficient. If the support of your distribution is 0, 1 to the n, then the optimal sample complexity for identity testing requires like exponential number of samples in. And since quantum advantage samplers generally output like n bits, then it's going to be way too inefficient to verify them. So our little lamp is sad. This is identity testing is useless. It's too inefficient for us to use. Yeah. And so our approach, essentially, we could still hope to achieve a good enough distribution verification that might be efficient. So in particular, we're going to relax our definition to instead of requiring instead of letting the adversarial distribution G be arbitrary, we're going to restrict it to efficient Turing machines. So that is, G will be like a sampler described by some Turing machine. Some classical Turing machine. Well, you could also think of quantum Turing machine. I'm still being vague about this point. Yeah. But yeah, for the purpose of QAS verification, classical adversarialism. Right? And so the idea is, if we restrict the class of distributions that we're worried about avoiding, if we restrict the class of distributions that we care about fooling us to only those that can be produced efficiently, then maybe distribution verification will be easier. And the idea is that this is good enough for our purposes. So if we use an identity tester, which is secure against only efficient adversaries, then it's still going to be true that any distribution sampled from a classical computer will be rejected, because any distribution sampled from a classical computer will be far and will be produced by some efficient Turing machine. But there's another kind of like bigger problem. So even if we could get efficient distribution verification or just efficient identity testing, secure against efficient adversaries, it's still not really enough for the purposes of verifying distributions, and in particular for the purpose of QAS. And the reason is the following. So our security notion specifies explicitly that the distribution should output, that the adversarial distribution has to output T, like kind of IID samples. But this is not true in the real world. Eyes might have her quantum computer output just like a whole bunch of correlated samples, x1 through xt, which would be a problem because maybe she can output correlated samples that the verifier thinks look like they're quantum, even though they're produced classically, which would be bad. And so we would really like to have an identity test or have a distribution verification that will accept samples from the honest distribution and reject even correlated samples from an efficiently generated bad distribution. And so to handle such adversaries, we're going to define distribution verification to essentially be an identity test which is secure against efficient but adaptive adversaries. So correctness will be the same. And for security, we're going to require that for all efficient adversaries, would produce x1 through xt. So they can produce t samples at once. And which are sufficiently far from the true distribution. And by sufficiently far, I'm going to mean that a random marginal of G has statistical distance from D. That is, if you were to run G to produce x1 through xt, and then pick a random one of these, that distribution should be statistically far from D.
I'm a bit confused by this distinction, because even if you have correlated samples, let's say you fix a window T, right? You can treat the whole distribution as over these windows of length T, right? So the IID case would just be make a product with the individual probabilities, and then the correlated case would be you have some other distribution over these length T sequences. So why is correlation special? I guess is what I'm saying. It's also, I guess what I'm thinking is it could just be an instance of the previous case where you just have these two distributions, and you want to test them.
Right, but the problem is, yes, yeah, you could imagine just like a one, if you only have like one sample for the identity tester, if the identity tester is only allowed to use one sample, then the definitions are the same. And the problem is that we just can't do identity testing. Like we're not going to be able to do distribution verification with the parameters we want using only one sample. And with more samples, you really want this kind of like adaptive function. But yeah, for any sufficiently far G, which is far in its marginals, we're going to require that the verifier accepts with probability at most essentially 1 minus epsilon plus some small error where epsilon was the distance. And this is because this is kind of the best you could hope for.
You cannot get like negligible error.
Yeah, you can't get negligible error because if this, for example, you can imagine that G literally is just exactly D with probability epsilon. And so therefore you're going to accept with probability at least. Or you can imagine that G is exactly D with probability 1 minus epsilon, and you'll get this distance, but your verifier will definitely accept with probability epsilon in that case. For the non-adaptive case, you can get negligible, but it's kind of not.
So this is a very least requirement, I guess, if you're going, like, if epsilon is small, then this sort of security isn't a very strong guarantee, right?
Yeah, so I guess if epsilon is small, if G is like very close,
Yeah.
then you're not going to be able to tell the difference that well. So yeah, this is true, but this is also just like generically true that if you have two distributions that are close, they're like already epsilon indistinguishable. For the purposes of QAS, since we said that like classical computers are very far, then like epsilon is going to be like 1/2 the n or something like this. In which case, this is like a really strong guarantee. Or epsilon is going to be like 1 minus 1/2 the n. And so this is a very strong guarantee. So I want to say one thing is that the verifier here is going to get some information bounding the ability of G. So in particular, we're going to allow the verifier to depend on both epsilon and the runtime of G. So the verifier will only work against distributions that run in time less than some particular G.
Is that a problem for the EOT application?
Yeah, I mean, it depends how you want to like. Yes, yes, and
For
sometimes.
full POTV on a single verifier, right? In some sense.
Yeah, it's not going to get you like the best thing you could possibly hope for. This is true. But this is what we can achieve.
Is there some kind of barrier for the general case where you have like a single verifier, but for G, okay, impossibility?
Is there an impossibility? There's like an impossibility in the sense that I don't think so. I think you would just need to make like stronger assumptions. Uh, like if P equals NP, for example, you should be able to do it up to arbitrary. Okay. No. No. But he does not equal NP. So. Okay. So yeah, the main question of our work is when is a distribution efficiently verifiable? There are different variants of this question depending on whether we allow the distribution to be like what we mean by efficiently samplable, whether it's a sample by like a classical Turing machine or a quantum Turing machine, or even like a distribution over quantum states that is a mixed state. We're going to consider all of these things. But there are more that you could also consider beyond the ones we discussed. All right. So what do we show? So our first result shows that if one-way functions exist, then every efficiently sampleable distribution that has like sufficient randomness is not verifiable. So this is kind of like a rough negative result. It's kind of impossible, where sufficiently random means more than n to the c min entropy. Yeah, that's not great. We cannot verify distributions because one-way functions exist. That's sad. And I know I, as a cryptographer, like to assume that one-way functions exist, but maybe they don't. So we're going to show this is actually kind of tight. If one-way functions do not exist, then every single sampleable distribution is efficiently verifiable. And so this is kind of like a Pessi-land result, where like just from the assumption that crypto does not exist, we get something useful. We can verify distributions. You can also think of this as like a lower bound in the sense that if you have a distribution which is not verifiable, then you have a one-way function. So we may also consider the quantum setting. In particular, we could hope that if some quantum cryptographic primitive does not exist, then every quantumly samplable distribution over classical strings is efficiently verifiable. We can ask the same for like quantum distributions over quantum states. That is, every sampleable mixed state is efficiently verifiable if some quantum cryptographic primitive does not exist. And we fill in these blanks. We show that if one-way puzzles do not exist, which are a primitive that I'll define later, then every quantumly-samplable distribution is efficiently verifiable. And in the quantum case for the quantum states, we show that if like weak EFI does not exist, which I am not going to define, but essentially, if you know what EFI is, it's EFI with like a very, very weak security parameter. But if weak EFI do not exist, then every sampleable mixed state is sufficiently verified. Unfortunately, we do not get the other direction as we do in the functions case. Possible. Okay. We will also get some bonus results. So the first bonus result is kind of a little silly. It just says that unconditional, it's an unconditional result. It says that we have, oh, my handwriting on this slide is so bad. We have a non-interactive protocol for certifiable randomness with a classical prover and an inefficient verifier. So I'll define what this means later, but this is very odd. And our second bonus result is that we will show if there does not exist one-way puzzles, then there is a universal verifier for QAS. That is, there is one particular verifier that will verify whether whatever it's been fed into is a quantum advantage sample. So any questions about the results from quantum techniques? So I'll give proof instructions for all of our results. If I run out of time, I may skip over.
Maybe the classical are the most interesting,
Yes.
because they're the most practical, I guess.
I mean,
I don't understand these one-way puzzles or really have a relevant, personally, I don't know where they're used. Like one-way functions are central the cryptography, but what are these one-way puzzles? Others like.
They're just like a quantum version of one-way functions, essentially. Like one-way functions are like the kind of central object in classical cryptography.
Yes.
And so if you like look at quantum cryptography, it's like the version of one-way functions for quantum. It's like the primitive that would be implied by all quantum cryptography. Uh,
And it's something that can exist even if P isn't.
so yeah, no one-way puzzles existing is like a slightly stronger assumption, but it's morally very similar to no one-way functions. But yeah, I will focus on the classical techniques regardless. Okay, so as a warm-up, I'll start by showing that if one-way functions exist, then distribution verification is impossible for any distribution. So in particular, let D be the sampler for some classical distribution. So we'll think of D as like some Turing machine that will take in some randomness R, and on a random R, we'll output a sample from the distribution. And let G be any pseudo-random generator. Then if we look at the distribution, that's just D applied to G applied to some new smaller randomness R. This distribution is going to be very far from the original distribution. Essentially because this is going to have much less min entry.
So these two R are different.
Yeah, they're different lengths, I guess. Yeah. So this R will have to be smaller than like the min entry of this distribution. But at the same time, these distributions are indistinguishable, so there's no way for a verifier to tell them apart. So therefore, distribution D cannot be verified. And that's the full argument. So if only functions exist, then you cannot do verification. Should not be that surprising, but that's the case. So next I'll focus on kind of our main classical result. Yes.
So for the previous theorem, it says for sufficiently random distributions.
Yes.
Why does
So if the min entropy is too low, then you can just learn the distribution with the polynomial number of samples and then verify. And then just like check if it's exactly equal to what's produced by the Turing machine. Like imagine a constant distribution. You know, if your distribution is just like it's always zero, then if you see somebody just say 0, 0, 0, 0, 0, you're like,
Oh, that's
that's
because when at a PRG, the two distributions are still not far from each other.
yeah, yeah.
Okay.
And that's the cryptographic security RNG.
Yeah, not the complexity. So next I'll focus on the classical result that if one-way functions do not exist, then every samplable distribution is verifiable. So I'll give a look ahead. The technique is not going to work generally, but it's a slightly easier approach. But regardless, the techniques that we use here are going to give the like bonus results. The techniques here I also think are just kind of like valuable to know and useful in general. So in particular, we're going to rely on something called Kolmogorov complexity. Kolmogorov complexity is a metric on strings, or it's not I guess technically it's a metric on strings. Essentially, the Kolmogorov complexity of a string X is the length of the shortest Turing machine that outputs X. Okay. So as an example, the Kolmogorov complexity of 10, 10, 10, 10 repeated 1,000 times is going to be the length of the Turing machine, which is just like some code, output 10, 1,000 times, which in this case is a string of length 20. So the Kolmogorov complexity of this value is going to be 20, give or take some constant factors. Meanwhile, the Kolmogorov complexity of a really, really long random string, which is completely random values, is going to be roughly 1000 because there's no short description. So Kolmogorov complexity is like length of the shortest description of the string. And kind of like a useful fact that we're going to use is that if you have a sampleable distribution T with high probability over the distribution, if you take a random sample from the distribution, the Kolmogorov complexity of that sample is going to be like a really, really good heuristic for the probability that the distribution outputs that string. The Kolmogorov complexity of X is going to be approximately log 1 over probability that T outputs X.
That's the information content.
Yeah.
What's the machine that achieves this?
So the machine that achieves this is going to be the machine that
Machine with B.
it's going to be essentially the machine for D that takes also in as description like where in so what you do is you write down the like PDF of the distribution in sorted order, which you can compute from D. And so then your machine, your description of the machine is going to be D plus like where in that list X appears, which is going to like roughly scale like this.
The lower bound is probably not that.
This is it's like counting argument. Like if you think of like a random, there's a counting argument. If you think of like a random string, for example, this is going to have high Kolmogorov complexity just because there aren't that many Turing machines of small size. Right. So, but this intuition led to the following idea from Aronson in 2014, which is that you can check whether a sample comes from a distribution that you know of by comparing its Kolmogorov complexity and this value log 1 over probability that D outputs X. And so in particular, Aronson came up with like essentially an inefficient distribution verification protocol, although he didn't put it in these words. So essentially how it will work is the verifier will take in samples x1 through xt, and it will output 1 if and only if this like log 1 over the probability that D outputs x1 through xt altogether is less than or equal to the Kolmogorov complexity of x1 through xt plus some constant.
And how is that complexity K found in practical play?
You can. It's uncomputable. So this is a downside of this verifier. You can't actually run it even like inefficiently.
The fundamental for verify.
It's a mathematical, like the purpose of his reason for defining this was to show like relationships between like sample complexity and like search complexity of like complexity classes, in which case it didn't really matter whether or not this was something computable. So, but by the previous reasoning, this will be true for honest distributions because this value and this value will be pretty much the same. And for a bad distribution, we know that its Kolmogorov complexity of the sample will be less than or equal to log 1 over the probability that the bad sampler outputs that long string, and which, because they're far, will, with high probability, be much less than the left hand. And so we'll reject. And so this is the verifier that we get, which is great, but as you were saying, we like have no way of implementing this. It's not just inefficient, it's uncomputable. So it turns out, though, our goal will be to make it efficient. And it turns out that if one-way functions do not exist, we can at least estimate the left-hand side using something called probability estimation. Okay. So the probability estimation says, as a result, classic result from 1989, it says that for all distributions D, there exists an estimator such that with high probability over samples from D, the estimator applied to X will be very, very close to this value negative log probability that D outputs X.
So this estimator needs something to train on
No.
a bunch of observations.
No, it doesn't. It knows the circuit for D.
Okay, oh, this is some existence, you don't know to actually.
Yeah.
Use test.
I mean, its existence, there's also like something, like you can imagine est instead of like just existing est could take in the description of the Turing machine D as input, and then there's some formula to come up with the estimator based off of this and something that picks on.
Is it like black box on D or like or black system D?
Black box on D, but it doesn't require pulling out the randomness.
Doesn't require.
It does require pulling out the randomness. Essentially, this like
You gotta set to random itself. That's what you mean.
It's like black box on queries to D. Essentially.
But in general, if I give you a sampler, I tell you estimate the probabilities, that's very difficult.
Yes, yeah, but this is, you could think of D as like, it's not, this estimator has the ability to call D on any randomness it chooses. It gets to like pick randomness to query the sample on. It's not like it doesn't know the underlying, essentially. It's much stronger than like query access, knowing the Turing machine description of the sample.
I guess it's query access in the sense that you see the input as a random take plus the input, right? You have to set the whole thing in the query.
Yeah, you get to set the like random table. Yeah, probability estimation in general is very hard with sample access, but if only functions don't exist for efficient distributions, you can still do it without like, since you have something much stronger than sample access, you have like the description of the code.
So what's this with high probability, which you're actually saying? If you generate a random sample and you run your estimate. So basically this is saying that your estimate is only good for the likely outcome.
Yes, exactly.
Okay, that makes sense.
But it's actually a little bit better than that because we get one-sided error, which is that even for unlikely outcomes, your estimate's never going to like underestimate this negative log probability. So you get one-sided error. So for likely outcomes, you're going to be right. For unlikely outcomes, you're always going to give an overestimate.
Or rather, an underestimate of the probability.
Underestimate the probability, yeah. Okay. So this is great. We can estimate the left-hand side of our verifier. We still need to estimate Kolmogorov complexity because uncomputable. That's not great. So what's our solution? We're going to swap out Kolmogorov complexity with like a very, very related metric. This related metric is something called UKT of X. It's like essentially universal probability is the most related thing. Formally or informally, it's going to be like negative log of the probability that a random Turing machine outputs X. A little bit more formally, you could consider the experiment where you take a random Turing machine as like a description of some random string of length t, and then you're going to run the universal Turing machine on that description for t steps. And this will produce something, and you're looking at the probability that this distribution produces it. And that's going to be the UKT of X. UKT of X is like very, very related to Kolmogorov complexity. And in fact, the limit as t goes to infinity is equal to Kolmogorov complexity.
For what distribution over T lengths?
This is pick any universal Turing machine, and then the distribution over p times is going to be the uniform distribution over strings. It turns out that it actually doesn't really matter, like what universal Turing machine you look at.
I'm not worried about the universal, I'm just wondering what is pi, or yeah, what is pi sample?
Yeah, uniformly random string.
I guess some samples will not be like Gaussian machines or so, but it's not a problem.
Yeah.
So you said in the limit it equals to the Kolmogorov complexity, but is there no quantitative connection?
Like for not limit?
Yeah.
No. Yeah, they should be like most of the time close. Yeah. But yeah, using UKT, all of the arguments that Aaron had made still work. It's still roughly equal to this like log 1 over a probability, blah 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 blah. So we're good. We can just replace K with UKT and be fine. And also, using probability estimation, if one-way functions don't exist, we can use probability estimation. Since this is literally just like the probability that some particular distribution outputs a string, we can then estimate UKT. In particular, this estimator is going to work for X produced by any samplable distribution with high probability. So the order of quantifiers is the following. There exists a single estimator such that for all samplable distributions D that run in time less than T, with high probability over D, the estimator will be close to the UKT difference. Does the estimator take the code of the? No. The estimator is completely agnostic to the code. The like moral reason behind this is because all Turing machines are going to have like constant overlap with this like universal distribution. Because you can always imagine that the Turing machine just has like a stop symbol and then a bunch of things. So if they have a Turing machine of length, C, then there's going to be like of strings of length 0, 1 to the T, 2 to the T minus C of them will agree. And so this gives us our final verifier. Our efficient verifier will simply run Aronson's verifier. Will replace this log 1 over probabilities and this UKT with the efficient approximations you get from not having one-way functions. And so if D is good, then the approximations are going to be right, and we will pass verification. If G is far, well, then the value of UKT will be correct, since this works for any samplable distribution. Note that the output of G will not necessarily be from D. These could be like these like low weight samples. But regardless, this left-hand side is going to be lower bounded. And so the test will work. And I just want to make it clear that this like one-sided error is critical. Yeah. So this is the classical setting. I know that people said that they weren't as interested in the quantum setting, but I want to talk a little bit.
I didn't say that. Don't misunderstand. I was just wondering for practical relevance. I was clear about the one-way functions for cryptography, but unclear about puzzles for quantum. That's all. I think it's interesting to clarify that.
Okay, I guess like one reason to care, like the quantum results, essentially one way of thinking about them is that they say that if P equals PP, you can do all these things. So if there's some complexity assumption that lets you do distribution verification, that's like an important complexity assumption for people in quantum. But I'll define it a little bit more. I don't know if I'll get to the actual proofs of quantum stuff, but I want to say at least what goes wrong, especially because it will motivate our bonus results. So I'm going to focus on, before I talk about the quantum setting, I'm going to define something called the one-way puzzle, which, as I was saying before, is like kind of the quantum version of one-way functions. So they're very important for quantum people, and they're non-existent. So one-way puzzles imply that P does not equal PP. So if you can think of anything that says one-way puzzles don't exist with, you can like match that or something like this efficient. Okay. So one-way puzzle is a single sample, a quantum sample, which is going to produce two classical strings, K and S, such that given S, which is going to be the puzzle, it should be hard to sample from the conditional distribution. This is essentially just like a quantum sampler version of something called a distributional one-way function. If you know what that is, it's something that's equivalent to one-way functions. And one-way functions imply one-way puzzles, imply useful quantum cryptography that we would really like to have. Okay. So, now that I've identified the complete player, the definition is not going to really matter that much for this talk. So if you didn't catch it, it doesn't really matter. Just think these are like quantum one-way functions. So we can ask, like, how would we attempt to generalize our results? And so note that like UKT of X only talks about like the probability that classical Turing machines output X. And so it's kind of useless if you're allowing our samplers to be quantum. But we may as well define a quantum version. Let's define QUKT of X being negative log of the probability that a random quantum Turing machine outputs X instead of a classical Turing machine. So the same definition as UKT of X, but with quantum instead of classical Turing machines. Turns out that if you don't have one-way puzzles, then just as before, we get probability estimation for quantum samplable distributions. So one-way functions are equivalent to the hardness of probability estimation for classical distributions. One-way puzzles are equivalent to the hardness of probability estimation for quantum distributions. And just as before, probability estimation also gives us an estimator for QUKT. It seems like everything should just work. But the big problem is the following. This estimator does not have that one-sided error that I was pointing out was so crucial. So the probability estimation we have, if you're doing the no one-way puzzles form of probability estimation, then it could be the case that you're just like very, very wrong on rare samples. And yeah, I don't know how to get one-sided error. It's a good open question. This actually comes up a lot in this area of like quantum crypto. And the key reason is essentially because we do not have this technique that we have in the classical setting where you can pull out the randomness and look at the like random input by itself. So we need new tech for the quantum setting. I don't think I'm going to actually have time to talk about this new tech. What I will talk about is the kind of bonus results that we get by looking at the techniques in the classical setting. Okay. So I'm going to first talk about this result on like unconditional certifiable randomness. So what is certifiable randomness? This is like a protocol whereby we want to test whether we're really given random strings by some prover. So in particular, it's going to be a pair of prover and verifier, where the verifier will accept whatever string is output by the prover with high probability. And security says that if you have any bad prover, P prime, then the conditional distribution on P prime, conditioned on V succeeding, should have high entropy. That is, if the verifier accepts, then at least the conditioned on the verifier accepting, you have verifier accepts implies that whatever it's accepting is random. And this is, useful in the real world because we never know whether somebody's really giving us real random numbers or fake numbers. So we really hope they are giving us real numbers. And we're going to allow the prover here to be some sort of quantum circuit. Because this morally should be impossible to do classically. And we're going to allow the verifier to be inefficient. And so note that in the non-uniform setting, we like really, even if we allow interaction, we really need the prover to be quantum. Because otherwise, we could just have a fake prover that hard codes the randomness of the honest prover. So if you have a classical prover, if the honest prover is classical, then we could just like pick some input, some set of randomness, and then just run the prover with that randomness, and it will fool verify, but not have any randomness inside. Okay. In the non-interactive setting, which is going to be the setting we're considering, this is only possible against uniform adversaries, because a non-uniform adversary could just hard code something that the verifier accepts. But it's not immediately obvious, at least, that in the non-interactive setting against uniform adversaries, you actually need the prover to be quantum. maybe it's the case that you could have a classical prover. There's no like obvious counterexample. So note that the prior work built such like a non-interactive, unconditional certifiable randomness protocol in the random oracle model with a quantum prover. So you have a quantum prover that does something, makes some sort of like random oracle queries, and then outputs some string, and then an efficient verifier is like, oh yeah, that's got to be random.
Which paper?
BBF +1. I will. I don't know. I can pull it up. I can. It's like with Sam Gunn and Bill Pfefferman and this paper. Right. Yeah. So in this work, we show that for at least the definition they achieve, certifiable randomness can be achieved unconditionally, non-interactive static within an efficient time. Yeah. So in particular, our prover is going to be a uniform distribution, and our verifier will just check whether this quantum Kolmogorov complexity is big. And kind of the intuition here comes from this fact from 2004, actually, that like Kolmogorov complexity is like kind of this approximate is not actually like an approximately equals, but it's like kind of has a deep relationship with at least Shannon entropy. We're talking about min entropy. This is talking about Shannon entropy. But regardless, Kolmogorov complexity is like deeply tied to like information denseness, which is like an entropy metric. So if the Kolmogorov complexity is high, that really should be the case that the sample is random. But we state it formally and in the same kind of language as certifiable randomness. So I kind of point out that previous results kind of miss, but this is just possible. And note that our prover here is like a classical string. It's not just a classical prover, it's literally just the uniform distribution. So you can really just like test whether samples have high entropy and random strings have high entropy. I'll give like a 2-line proof of this statement. So let P prime be any prover. Well, clearly the P prime conditioned on the accepting. All outputs must have its support, must have high quantum Kolmogorov complexity by definition. The quantum Kolmogorov complexity is equal to log of 1 over the probability that P prime outputs X. And so the probability that P prime condition on D outputs X has to be C, which is exactly the same thing as saying that the min entropy of P prime of D has to be D, since this holds for all X. And so we get a result if only puzzles do not exist. Oh, sorry. This is, so yeah, so we're done. This is the unconditional certifiable randomness protocol with full proof. It's fairly simple. But surprisingly missed by at least the certifiable randomness.
That random oracle paper gave you a lot of work, right? This is
Yeah. They do a lot of work, but it's not. But I mean, there are plenty of other papers on certifiable randomness doing cool things, such as like efficient verification and whatnot, and this does not achieve any of that. Right. So the second bonus result that I'm going to talk about is the universal verifier for quantum advantage sampling. So if only puzzles do not exist, formally we'll show that there is a single verifier var, which accepts every quantum advantage sampler and rejects all classically samplable distributions. And so, just caveat, these are time classical sample distributions that have to, run time less than some fixed poly, blah, blah, blah. But the key idea is that if D is a QAS, and if it's sampleable quantumly, but not classically, well, then it must be the case that its quantum Kolmogorov complexity of a random output should be much less than the classical Kolmogorov complexity for This is because it has a short quantum description, but no short classical description. And so to verify, we'll just estimate both the quantum Kolmogorov complexity and the classical Kolmogorov complexity and compare them. So our verifier will just estimate QUKT, estimate UKT, compare the two, and output one if and only if the QUKT is much smaller than the UKT. For the QAS, it's going to be the case that QUKT is much less than UKT, so we'll accept. So for any quantum advantage sampler, the verifier will accept. But for any classical distribution, these two things are both going to be equal to log of 1 over the probability that the output's x, and so they'll be the same, and so we'll reject. So that's it. We proved the claim. There is a single verifier that accepts every quantum advantage sampler and rejects all classically samplable distributions. So there's a lot more work that goes into showing the same results for the quantum samplable, the full verification result for the quantum samplable setting and for the quantum state setting, but I'm going to skip over all of this. And go right to the open questions. So the first open question is, can we get this like one-sided error for probability estimation from no one-way puzzles? This is like a kind of, I would really, really like this to be possible. I have a feeling the answer is no. But it would be very nice. It would make a lot of things much easier in quantum. The second question is like, can we get this converse in the quantum settings? Like, can we say that if we have these like quantum cryptographic primitives, then there's a distribution that's hard to verify? I have some ideas, but also a little bit challenging. Third question is like, can we come up with other cryptographic conditions for like other property testing problems besides like identity testing or I don't know, just any sort of identity testing problems? Yeah. And then 4 is like, right now we're considering adversaries that are either classical Turing machines or quantum Turing machines. But there's many, many different kind of classes of adversaries that we could consider. What's the kind of connection between cryptography and security against like other sorts of versions? So maybe like log length, log space Turing machine, something like this. Maybe this gives you something.
I guess you also don't have any results about non-uniform.
Yeah, we don't have any results about non-uniform adversaries. I mean, the kind of non-interactive setting we're considering makes non-uniform impossible, but you can imagine
Like two massive.
Yeah, two massive objectives. Thank you.
Question. So how would you characterize, maybe taking a step back, the level at which these contributions live? Is this more of a complexity theoretic fault? Do you think these are practical? So property testing, for example, many of these algorithms do focus on practical tests. Some of them don't. Some of them are massively complicated and rely on all these constant factors and these process procedures that not obvious how to reify them, but for these specific verification techniques, especially for the classical stuff.
Yeah, so
are they direct or indirect when it comes to graphical algorithms?
I guess mostly I think of these results as lower bounds, kind of. Like saying that, oh, if you had something that was hard to verify, if you have something that you think is hard to verify, then this really must like imply cryptography. And this kind of is also nice in the sense that like people have candidates which they think are hard to verify. So these like, now anytime somebody thinks of a candidate that they think should be hard to verify, this is like a cryptographic object, which is nice. It lets you build cryptography from things that you think are hard in kind of a different way. Also, I would say that there is some small iota of like implementation, like practice that you can get from this in the quantum advantage setting. In particular, the like no one-way puzzles assumption. As I said before, like you can break this with PP. If you can do post-selection, this is like a hard task in quantum. But if you can do post-selection, then you can verify these kind of quantum advantage samplers. And these existing quantum advantage samplers are kind of like in really, really small n regimes. So this does give you like a not efficient verifier, but maybe more efficient than like 2 to the n, um, which still might be used. Not that I'm saying this will be used, but like it could conceivably be used by uh, people who like run these really small quantum advantage experiments. You have any questions on Gene?
No,
Specular speaker there.